So we're revisiting the pancakes. Suppose we have 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder. How many pancakes can we make? Well, we've got our recipe. A cup of flour and 2 eggs and a half teaspoon baking powder would make 5 pancakes.
15 pancakes, because the 1 cup of flour, the cups of flour, the 3 cups of flour is your limiting agent or reactant.
We're going to run out of an ingredient, right? And it's hard to just look at that. I think you're right. It's hard to just look at this and say, oh, well, duh, it's this, right? The thorough way to do this is to see, well, 3 cups of flour would make how many pancakes? 15. So 3 cups of flour, and there are 5, I'm going to call them PCs, pancakes for every 1 cup of flour. So that would give us 15 pancakes. And we have, what, 10 eggs? 10 eggs, we get 5 pancakes for every 2 eggs. So that gives us 25 pancakes, right? So that tells us, you know, when we're making them, the 3 cups of flour, we're going to make 15 pancakes, and then we're out of flour. We can't make more. And then let's look at this teaspoon of baking, 4 teaspoons of baking soda, powder, sorry. So 4 tisps of baking powder, and there is 5 pancakes per half tisp of baking powder. So the 4 divided by 1/2, well, I don't want to do that. It's 20, yeah, 40. 40 pancakes. You were right, 15 pancakes. So the process here is you look at your different ingredients and you figure out how much product could I make if I use all of that up and I had enough of everything else. And you do that for each thing that they're telling you about. And then out of those, you choose the smallest one, right? Because we're making pancakes, we have 10 pancakes, we have 15 pancakes. We can't go any farther because we ran out of flour. So that's how much you could make. And that's called the theoretical yield of pancakes. Because it could happen that you drop one on the floor, right? And so, yeah, you had enough stuff to make 15 pancakes, but you didn't actually get 15. Or somebody sneezed on one, or, you know, who knows? Who knows what could happen?
Wait, what do you call those? Are they a limiting reactant?
It's a limiting reactant.
Okay.
So here
Oh,
you
yeah,
go. There you go. You predict the future. So if it were a chemical reaction, we would say that the flour is the limiting reactant, because the flour would allow us to make 15 pancakes, the eggs would allow us to make 25, and the baking powder would allow us to make 40. We can only make the smallest amount. So that's the limiting reactant. The limiting reactant is the reactant that limits production. Okay? The theoretical yield is how much you could make given your starting quantities, provided that everything went perfectly. Does anything ever go perfectly? No. Something always happens, right? Always. And then we have a concept of percent yield. So the percent yield allows us to compare our actual yield with our theoretical yield. The actual yield is how many pancakes you actually made. So, you know, there was a phone call and 4 of those pancakes on the griddle got burned. They were ruined. We had to throw them away. So our actual yield is only 11 pancakes. So we only ended up with 11. That is the actual yield. The actual yield is the amount that you actually make. In a chemistry problem, they have to tell you the actual yield. Okay? In the lab, what you make is your actual yield. You're measuring that. But there's not really a way to predict what that's going to be. We can, the percent yield would help us to predict in the future. So the theoretical yield down here is from the calculation. So the theoretical yield is calculated. The actual yield is measured, or in a homework situation, test situation, it's given to you. And then the percent yield is the part over the whole times 100. The actual yield over the theoretical yield times 100. So we got 73% of our theoretical yield. That would allow us to predict in the future, if we had to make pancakes for the football players. And then we could say, well, actually we need to plan on making more because some of them are going to get ruined, right? And so we'll up our production. And this happens a lot in industry because there are various reasons why the actual yield is not equal to the theoretical yield. And they don't all have to do with people screwing up. Some of them do, but some of them don't. And so if you want to end up with this certain mass of product, how much do you have to start with?
So you can never go above the theoretical yield. It's always below, correct?
You're predicting things again.
Oh.
So the question is, you can never go above the theoretical yield, right? Well, actually, so we'll continue on here and we'll get to that in just a second. The actual yield has to be determined experimentally. It depends on reaction conditions. The actual yield is almost always less than 100%. Almost always. And reasons are some of the product doesn't form, or some of the product is lost in the process of recovering it. Maybe it's a precipitate in a solution, and when you filter it, some of it goes through the filter paper or something like that. And I think, is the next slide? No. Okay, so let's talk about it here. How could an actual yield be greater than a theoretical yield? I mean, can you make more product? Could I, if I had that many ingredients, could I make 17 pancakes if I only have enough stuff for 15? If I made them smaller, but you can't do that with. That's why I don't like the pancake thing. I personally do a bicycle factory. I think of a bicycle factory. If you had, let's say, 10 wheels and 10 bicycle frames, how many bicycles could you make? 5, because you only have enough wheels for 5 bicycles. Is there any way you could make 6 bicycles? Well, if you couldn't count, but really, no, you couldn't, right? So how could you possibly end up with a product that is more than it's supposed to be?
10 unicycles.
10 unicycles. Well, if your reaction conditions were incorrect and you made a different product than you anticipated, that would cause a problem. And that's like, oh, a bicycle has 2 wheels? I thought it only had 1 wheel, somebody being really stupid. And, well, gosh, I made 10 unicycles. The other thing, which is more common, is that you either have a contamination. So, I think I told you I had I did that gravimetric sulfate, the barium sulfate lab that we did last week. When I did that in quant lab in college, we're down to the end of it, and a fly fell into somebody's crucible and got ashed with the sample, right? So that increases the mass of the sample, right? And so then all of a sudden now you've got 105% yield. Well, did you really make more than you thought? No, you had to contaminate. So what he did is he went around the building and caught 10 flies and ashed them and found the average mass of an ashed fly and subtracted that off. And that was faster than doing the whole experiment over again. Anyway, so that's something that can happen. The other thing is if you're collecting a precipitate and you filtered it and you don't completely dry it. if it's a little bit wet. Now you've got water on your sample, that's going to make it weigh more. So it's possible to end up with a percent yield that's greater than 100%, but it indicates that something went wrong. Okay? It indicates that there's something else going on that we should look into. So here's the summary slide. The limiting reactant is, or the limiting reagent is the one that is completely consumed. So that's the one that gets all used up. And in our pancake example, we used up all the flour. We're going to have some eggs and baking powder left over. And in cooking, that's often the way it is. You set out to make a cake or something. You don't have the exact amounts of every ingredient in your house. You've got extras of most of them. And then the theoretical yield is the amount that could be made based on the amount of the limiting reactant. So the way we figure that out, those two out, is you take all the reactants and you calculate the yield from them, and you pick the smaller one. The smaller one is the theoretical yield, and the reactant that gave you that is your limiting reactant. The actual yield is the amount you actually get. These terms are not meant to be cryptic. It's like the actual yield is how much you actually get. And the percent yield is the actual yield over the theoretical yield times 100. So when I don't mean to push through, oh, it did move. Why couldn't I see that? Losing my mind, what little I have left. So let's look at a chemical reaction. Titanium reacting with chlorine to form titanium 4 chloride. What are the limiting reactant and the theoretical yield if you started with 1.8 moles of titanium and 3.2 moles of chlorine? So 1, 2, 3 here are the little steps that we need to do. We need to use stoichiometry, which is this process of calculating amounts, to find the amount of product that could be made from each reactant, just like we did with the pancakes. The limiting reactant is the one that gives the smaller yield, and the theoretical yield is that smaller yield. Okay, so I'm going to make the directions go away through the magic of science and, it's not science, it's technology. So let's take these numbers, and we've got 1.8 moles of this and 3.2 moles of that. So on your paper, you should copy down the chemical equation and use that as a guideline. So that's what we've got, and then we're trying to figure out this. The theoretical yield, they're not telling us, they should tell us, what unit they want. I happen to have looked ahead, and I know that they want moles. So we're given moles, we're asked for moles, and so we think, well, our map, you told us the map was grams to moles to grams. And sometimes students get confused and they say, well, then this one must be moles to grams to moles. No. This one is easier, it's just the part in the middle. Okay? So sometimes I'll put a question like this on an exam and make it moles to moles because it's a lot easier, and then students will freak out and make it really hard and get it wrong to boot. No, I was trying to be easy on you, and you just took it the wrong way. So all we have to do is moles to moles. So what we're going to do is we're first going to look at the titanium, 1.8 moles of titanium. And this is a one-step process. 2 moles of titanium chloride and moles of titanium go down here. We look at the equation. There's one of each, right? So that much titanium would give us the same number of moles of the product. Okay? And don't be thrown off because that maybe seems a little too easy. It's okay, sometimes things are easy. Then we take our other ingredient, our other reactant, which is chlorine, and we convert that to moles of titanium chloride. Same process. The number in front of chlorine, though, is 2. 1.6, right? Did I do that math in my head correctly? Thank you. So we take each reactant, we calculate the amount of product, and then we look at them, which is smaller, 1.8 or 1.6? So, oh, 1.6 is smaller. This is the theoretical yield. Okay, and like on a lab situation where I'm actually looking at your handwritten work, you have to indicate to me which of those you're choosing. Okay, if you do it without the box, it's like, well, yeah, you had all the work there, but you didn't choose anything, and so it's not completely correct. So that's our theoretical yield. This is our limiting reactant, because it's what made the lowest amount. So you've got 2 equations here. You pick which one gives you the smaller number, you box it. That's your theoretical yield. Then you look back, you go, okay, here, I cannot see this for anything. Okay, so here, and then I'm going to just trace back up what gave me that. That's the limiting reactant. Okay? Yes?
So for the converting factors, you find those in the equation, right?
Yes. The 1 and the 2 come from the balanced chemical equation.
Okay.
Yep. And sometimes, students are trying to do some funny thing. No, that part's easy. You just take the number in front of it and you stick it in there. Any other questions? Here's another example. Consider this reaction. Sodium reacting with fluorine to make sodium fluoride. Just for grins, what kind of a reaction is that? Synthesis. It's a synthesis reaction. We have 2 reactants and 1 product. And what other kind? It's a redox reaction. We have a metal reacting with a nonmetal. So that falls into 2 different categories. Do we need to know that for the problem? No, we don't. But, it doesn't hurt to review things, right? So if you begin with 4.8 moles of sodium and 2.6 moles of fluorine, what's the limiting reactant and theoretical yield of sodium fluoride in moles? This is better. They're telling us that they want it in moles. So 4.8 moles of sodium and 2.6 moles of fluorine.
Sodium.
So, on an exam, these things are not going to necessarily come in this order where you know what kind of a problem it is. So how do you recognize, oh, this is a limiting reactant problem? They're giving you 2 quantities. Before we started this section, they only gave us 1 number. Now they're giving us 2 numbers. That's a hint. And then what we're trying to find is question mark moles. So we have to do 2 separate calculations. So 4.8 moles of sodium. And we need to find out how many moles of sodium fluoride we can make from that. Well, we look at the balanced chemical equation. Each of those has a 2 in front of it. And so that ends up being 4.8 moles of sodium fluoride. You may say, well, I didn't need to do that calculation. But when we get to grams, you will. 2.6 moles of fluorine. What? I did not do that. And moles of sodium fluoride over moles of fluorine. Well, there's a 2 in front of sodium fluoride, and there's no number in front of fluorine, so that's a 1. So this is going to get us 5.2 moles of sodium fluoride. If you stop there, you're not done. You have to look at those and say, which is the smaller one? Well, this is smaller. That's my theoretical yield. What's the limiting reactant? It's the one that gave me that. So this is my limiting reactant. Fun times.